Imagine boarding a flight in New York and stepping off in Los Angeles in less than 45 minutes, or leaving Delhi and arriving in Dubai in 20. That is the promise of hypersonic travel. Currently, every commercial flight you take operates entirely below the speed of sound, or Mach 1. Historical context helps show the scale of the challenge. The Concorde marked the peak of passenger flight by pushing that limit to Mach 2. Reaching the hypersonic threshold requires a massive leap in Mach 5, traveling over 6,125 kilometers per hour. At this speed, an aircraft covers 1.7 kilometers every single second, moving 5 times faster than the speed of sound. But achieving Mach 5 is not just a matter of adding more power. It requires overcoming a violent physical barrier that traditional planes are not designed to survive. A standard jet engine cannot function at these speeds. Simply scaling up the size or power of current designs results in immediate failure. This simulation visualizes the heat barrier. At Mach 5, compressing air generates friction up to 1900 degrees Celsius, instantly melting standard materials. A conventional fuselage would fail. Furthermore, the massive velocity of incoming air would immediately tear a traditional engine's rotating fan blades apart. At hypersonic speeds, the air needed to keep the plane aloft becomes a destructive force, hitting a literal wall of physics. To survive Mach 5, engineers use the ramjet engine. This architecture removes the greatest vulnerability of a jet engine by having 0 moving parts. This cross-section shows the engine's interior. Lacking rotating turbines, it relies entirely on the aircraft's forward momentum. It rams incoming air into a narrow chamber, building pressure naturally, mixing it with fuel and igniting it for continuous thrust. Because the airflow is so volatile, the engine and the airframe must work as a single aerodynamic system. The entire underside of the plane is shaped to funnel air directly into the ramjet intake. This process requires hydrogen fuel. Hydrogen is used because it burns rapidly enough to maintain steady combustion within the microseconds it takes for air to pass through the engine at Mach 5. The ramjet effectively turns the greatest problems of hypersonic travel, the extreme speed and pressure, into the mechanism that powers the flight. Japan's space agency, JAXA, successfully conducted a ground test of a ramjet engine designed for Mach 5 flight, moving this technology out of theory. Testing this hardware is a significant engineering hurdle, as normal wind tunnels cannot simulate the combined pressure and heat of hypersonic flight. JAXA utilized a specialized facility to blast a 2-meter experimental vehicle with hypersonic pressure and heat exceeding 1,000 degrees Celsius. To prevent the test vehicle from melting, scientists utilized advanced heat-resistant materials and thermal shields to protect the internal systems. Successfully surviving these conditions in a lab environment proves that the core engineering required for Mach 5 is physically achievable. The results from JAXA showed that internal temperatures remained stable, allowing the electronic control systems and the ramjet to function correctly throughout the simulation. While passenger travel is the primary goal, this technology also applies to global logistics, specifically the rapid delivery of cargo and emergency supplies across hemispheres. An emergency medical response could potentially reach a different continent in less time than it takes a standard jet to reach its cruising altitude. As the engineering matures, the 4,400-kilometer distance between New York and Los Angeles could effectively be condensed into a 45-minute flight. Reducing a 6-hour journey to under 45 minutes remains the next major challenge in aviation. The hardware required to reach that goal is now moving from computer simulations into successful, high-stress laboratory testing.